Unit 4, pages 115 to 118, Implicit differentiation. Much of our algebraic study of mathematics has dealt with functions. Earlier today, we talked about two different types of equations that relate x and y, explicit and implicit. Explicit equations in x and y are such that y is isolated on one side of the equation and it equals an expression that is totally in terms of x. When I look at an explicitly defined equation, I can explicitly tell if it represents a function or not. In other words, when I see y equals the square root of 25 minus x squared, I know that for every value of x, there's only one y, making this equation a function. When I see y equals plus or minus the square root of 25 minus x squared, I know that for every x, there are two y values, making this equation not a function. Implicit equations are very different. Typically, they do not have a y isolated on one side of the equation. Often there's a power on the y terms in the equation, and both y's and x's may appear throughout the equation. For example, the equation x squared plus y squared minus 2x plus 4y plus 16 equals 0 is that of a circle. Calculus can even be applied to implicitly defined equations. In this lesson, we will see how to differentiate those equations that are implicitly defined. We will utilize an alternate notation for the derivative. Instead of f prime of x, we will use dy dx. As calculus was developed by two different men, a blend of their notations has been accepted. Let's think about how we differentiate y equals the square root of 25 minus x squared. Then let's differentiate the implicit form of this equation, x squared plus y squared equals 25. So before we do that, I just want to point out this notation that we're going to start using a lot more often, dy dx. So the notation dy dx is very important because the denominator term dx tells us what we are looking for our function in terms of. Okay, and dy just tells us what we're differentiating. Okay, so we are differentiating y in terms of x. Okay, so we're going to use this information to differentiate these two equations. And both of these equations represent the same function. So we're going to first start with the explicit version of this function, which is y equals square root of 25 minus x squared, which we can rewrite as 25 minus x squared to the 1/2. Okay, so what I want you to do is I want you to differentiate that function. And when you do that, you should get the same answer as what happens when I differentiate our implicit function, which I will do on the right side. And as I differentiate this function, I will explain step by step what it is that I'm doing. So we have the function x squared plus y squared equals 25. So what I'm going to do is I'm actually going to differentiate this every single part the same way that we would differentiate if it was an explicit function. So the only new step that I'm going to add is I'm going to add that we're using this notation dy dx for each term, because I will be differentiating each term. So every time I see a plus or minus, if there's no multiplication happening, I will use dy dx. So I'm going to use dy, well, actually it's not dy dx in this case, it's actually going to be, for this first term, since we're not differentiating y, this is x squared, we're actually just u dx of x squared plus d dx of y squared equals d dx of 25. So I'm basically taking the derivative of x squared in terms of x plus the derivative of y squared in terms of x plus the derivative of 25 in terms of x. Okay, so the derivative of x squared in terms of x, we know how to find that. That's just 2x plus the derivative of y squared in terms of x. So this is where it gets a little bit different. So we're going to take this derivative how we normally would if y was x. So that's 2y. But because we're taking the derivative of y in terms of x and not x in terms of x, we're going to have this notation here, dy dx, because we took the derivative of y in terms of x. And then over here, we have dy dx of 25, which we know is just going to be 0. There's no variable, it's just a number. Derivative of a number is 0. Okay, so when you're implicitly differentiating, you want to have your final answer in the form of dy dx equals whatever else is happening. So what I'm going to do is I'm going to move everything to the right side so that my dy dx stands alone. So I'll have 2y dy dx equals negative 2x. And then to separate the 2y dy dx, I have to divide by 2y. So we have dy dx is equal to negative 2x over 2y, which we can simplify. So dy dx equal to negative x over y. And from our explicit function, we know what y equals, right? Y is equal to the square root of 25 minus x squared. So our final answer is that dy dx equal to negative x over square root of 25 minus x squared. So now we have the derivative function in terms of x after differentiating y. Okay, so now let's move on to page 116, where we look a little bit more closely at what dy dx can tell us. So we're going to consider the graph of the circle to the right and find the equation of the circle in its implicit form. So similarly to what we did in class today, we're going to find the equation of the circle. It doesn't give us much information, so what we're going to do is we're going to try to find the center of the circle, and I'm going to do so by just drawing a line down the middle of the circle vertically and horizontally. And where they meet will tell us where the center of our circle is. So the center is at 3, negative 2. And if we count how far from the center to the outside of our circle we go, we notice that our radius is 5. So when we write our equation, we know we have x minus 3 squared plus y, and since it's negative 2, it's going to be plus 2 squared equals our radius squared. So 5 squared is 25. Okay, so now we want to implicitly differentiate this equation. So going back to what we did on that first page, we want to find d dx of x minus 3 squared. Let's rewrite that. X minus 3 squared plus d dx of y plus 2 squared equals d dx of 25. Okay, so again, we're going to differentiate these the same way we're used to. The only difference is going to be when we differentiate that second term, because of the y. So if you look very closely, these are all chain rule problems, the first and second term. So the inside of my chain rule is x minus 3, and the outside is x squared. So the derivative of x squared we know is 2x, so we have x minus 3. And the derivative of x minus 3 is just 1. We're going to add to that, again, another chain rule problem. So we have 2 times y plus 2, and the derivative of our inside is just going to be 1. And since this is all y, we know we're going to have dy dx. We differentiated y in terms of x, which really just means we differentiated y the same way we would have differentiated x if y was x. And then the derivative of 25, again, derivative of a number is just 0. So our goal is to get the dy dx alone. So we're going to move what we can over to the right side. So we'll have 2y plus 2 dy dx equals negative 2x minus 3. And then we'll divide by 2y plus 2. So we get that dy dx equal to negative 2x minus 3 over 2y plus 2, which we can simplify to negative x minus 3 over y plus 2, which we can simplify again by distributing that negative sign to being negative x plus 3 over y plus 2. So our final answer here is that dy dx equal to negative x 3 over y plus 2. Okay, so what we're going to do with that derivative is we're going to complete the table below, finding the value of the derivative at each of the indicated points. Then we're going to draw the graphical representation, aka the tangent line, on the graph at each indicated point. So what's nice about implicitly defining or differentiating is that we can now take a full point, an x and a y, and plug it into our derivative to figure out what the slope of the tangent line would be at that point. So since our x in this case is 0 and our y is 2, we know that dy dx is going to be equal to negative 0 plus 3 over 2 plus 2, which is just 3 over 4. So that's our derivative at 0, comma 2. So if we go to our graph at the point 0, comma 2, we should be able to draw a line with a slope of 3, 4 to get the tangent line. So if we, using rise over run, we know we're going to rise 3, run 4. So if I were to draw a line here, that line will be tangent to the circle at the point 0, 2. Okay, and then we're going to do this a few more times. I'm only going to do the next 2 points, and then you'll finish the rest. So for 3, 3, we know that we'll have dy dx equals negative 3 plus 3 over 3 plus 2, which is just 0 over 5, which equals 0. So when our derivative equals 0, we know we'll have a horizontal tangent. So since we know we should have a horizontal tangent at 3, 3, when I get there, I know that all I'm going to need to do is draw a straight horizontal line, and that will be the tangent line. And then for 8, -2, that means that dy dx is going to be equal to -8 plus 3 over -2, 2, which is equal to -5 over 0, and dividing by 0 gives us undefined. And if our slope is undefined, because the denominator is 0, that means that we have a vertical tangent. So when we go to 8, -2, we should be able to draw a vertical line as the tangent on that circle. Okay. What I want you to do is complete the rest of this table. There are 4 more points. Identify if they're vertical tangents or horizontal tangents, and also sketch those tangent lines on your circle. Page 117. For this page, we're really just practicing how to implicitly differentiate. So we're going to practice, I'm going to do 2 problems. I'm going to do the 2 on the left side, and I'm going to leave the 2 on the right for you to do on your own. But the 2 on the left, start with the top. So I want to implicitly differentiate y squared equals 2x plus 3y. So what I'm going to do first is write what it is that I want to do. So I want d dx of y squared equals d dx of 2x plus d dx of 3y. Right, so because they're separated by an addition sign, I know that I can separate them into 2 separate terms. So on the left side here, we have y squared, so we're going to differentiate as if this was as if this was x. So we have 2y, and because this is y and not x, we need that dy dx. And that's going to be equal to the derivative of 2x, which is just 2, plus the derivative of 3y. So if we differentiate as if this was x, the answer would just be 3. But because we're differentiating y, we want to make note that we differentiated y in terms of x. Okay, so now, again, our point is to get the dy dx's on the same side. Right, we want to get them on the same side and alone. So we're going to move this 3 dy over to the left side. So we have 2y dy dx minus 3 dy dx equals 2. And then we can factor out a dy dx of both terms. So we have dy dx times 2y minus 3 equals 2. And then we can just divide by 2y minus 3 to get dy dx on its own. So dy dx equal to 2 over 2y minus 3. Okay. So moving on to the bottom problem on the left side, we have 2xy equals 3y squared plus 2x. So again, I'm going to rewrite what I need. So I need d dx of 2xy equals d dx of 3y squared plus d dx of 2x. So for this problem, if you look on the left side, we want the derivative of 2xy. If you look closely, 2xy is a product of 2 variables, which means we're going to need to use product rule for this problem on that left side. So if you remember product rule, you know that we're going to need the derivative of the first term, which we know is 2, right? The derivative of 2x is 2, times the second term, so which is y, plus the first term, which is 2x, times the derivative of the second term. So the derivative of y is just 1, but because we're taking the derivative of y in terms of x, we need to add that 2y dx by multiplying it. So that equals, and then if we look on the right side, derivative of 3y squared should just give us 6y, but y in terms of x, so we need dy dx plus the derivative of 2x, which is just 2. So if we simplify this, we get 2y plus 2x dy dx equals 6y dy dx plus 2. So to get the dy dx's alone on the same side, we're going to have to move some things around. So we're going to have to subtract the 2y from the left side and subtract the 6y dy dx from the right side. So we'll have 2x dy dx minus 6y dy dx equals 2 minus 2y. We can factor out a dy dx on the left side, and we can factor out a 2 on the right side. So let's do that. We have dy dx 2x minus 6y equals 2, 1 minus y. And then we need to divide by 2x minus 6y. So we'll get dy dx equals 2, 1 minus y over 2x minus y. We can factor out a 2 from the denominator as well, so we get 2, 1 minus y over 2x minus 3y. So our final answer, dy dx, is equal to 1 minus y over x minus 3y. Okay. So try the 2 problems on the right on your own to the best of your ability. We're going to move on to page 118. Okay, so for page 118, first 2 problems not only ask us to implicitly differentiate, but also to identify certain values that will either give us a horizontal tangent or a vertical tangent. So luckily for us, both problems have the same function. So once we implicitly differentiate once, we don't have to do it again. We just have to show our work for finding our answers. So for what values of x will the curve x cubed plus y cubed equal 4xy plus 1 have a horizontal tangent? Show your work and explain your thinking. So we want the values of x. So what that means is that we want actual numbers for x. So we're first going to implicitly differentiate. So we want d dx of x cubed plus d dx of y cubed equals d dx of 4xy plus d dx of 1. Okay, so to find this derivative, we know that derivative of x cubed in terms of x is just 3x squared plus the derivative of y cubed in terms of x will give us 3y squared dy dx, right? Y in terms of x equals, now here we again have the product of 2 variables, and thus we'll need to use product rule to differentiate. So channeling product rule, the derivative of that first term is just going to be 4 times our second term, which is y, plus the derivative of our second term, which is 1 dy dx, times our first term, which is just 4x. And to that, we're going to add the derivative of 1, which we know is 0. So when we simplify all of this, we get 3x squared plus 3y squared dy dx equals 4y plus 4x dy dx. So again, we want the dy dx terms to be on the same side so that we can isolate the dy dx. So we'll have 3y squared dy dx minus 4x dy dx equals 4y minus 3 squared. And when we factor out the dy dx, get dy dx times 3y squared minus 4x equals 4y minus 3x squared. So our final answer, dy dx equals 4y minus 3x squared over 3y squared minus 4x. Okay, so that doesn't quite answer our question. Our question is, when will this curve have a horizontal tangent? So if we look back to page 116 from the table, we'll notice that our horizontal tangent occurs when our derivative, our dy dx equals 0, right? So we're looking for when dy dx equals 0, which is really just when the numerator of our dy dx equals 0. So if dy dx equals 0, then 4y minus 3x squared equals 0, right? Because 4y minus 3x squared is our numerator. If that equals 0, then our whole fraction will equal 0. So what we're going to do is we're going to use that information to solve the equation. So we have 4y minus 3x squared equals 0. We're going to solve for y. So we get 4y equals 3x squared. So y equals 3/4 x squared. So because we now know what y is, and we want to know what our original curve will have a horizontal tangent, we are going to plug in y into our original function and then enter it into our calculator to find what x is. So we have x cubed plus, instead of y, we have 3/4 x squared cubed equals 4x. Instead of y, we have 3/4 x squared plus 1. So the wonderful thing about a calculator is that if two sides of your equation are going to be equal to each other, you can plug in each side into a different y function. So this can go into my y1, and this is going to go into my y2. And then I find where the two graphs intersect, and that occurs at x equals approximately negative 0.7693 and 1.7321. So at these two values of x, my function will have horizontal tangents. So now, for the second piece, we want to know in terms of y. So this is really important. We're not looking for actual values of x. We're looking for x equals, and whatever x equals has to be in terms of y. We want to describe the values of x for which this curve will have vertical tangent. So in order for this to have a vertical tangent, dy dx must be undefined. And if dy dx is undefined, then the denominator of my derivative should equal 0. So 3y squared minus 4x equals 0. So what we're going to do is we're going to solve that. So 3y squared minus 4x equals 0. We want to solve for x in terms of y. So we're going to have negative 4x equals 3y squared. So x is equal to negative 3 over 4 y squared. So our final answer is x equals, and our right side is in terms of y. So for this last piece of the notes, we're going to introduce a slightly new topic. So we want to find not the first derivative, but the second derivative of these functions. So what we're going to do is we're going to find the derivative, and once we get that answer, we're going to find the derivative of that. So when you see this notation d squared y over dx squared, this is just asking you to find the second derivative. You might also see it written as f double prime of x later on in this unit, but it's also just asking you to find the second derivative. So I'm going to do the problem on the right side, since that one is a little trickier than the problem on the left. So the problem on the right, we're given the curve x squared plus y squared equals 1, and we want to find the second derivative. So what we're going to do is we're going to find the first derivative. So what we want is we want d dx of x squared plus d dx of y squared equals d dx of 1. So the derivative of x squared we know is 2x. The derivative of y squared is 2y. But since we're in terms of x, we need dy dx. And the derivative of 1 is 0. Okay. So to get dy dx all by its lonesome, we need to do some manipulation. So we're going to have 2y dy dx equals negative 2x. So dy dx equals negative 2x over 2y, which we can simplify to just negative x over y. Okay, so dy dx equals negative x over y. Okay, so now we want the derivative of that. So what we're looking for now is d dx of negative x over y. Okay, so looking at this, we very clearly have a quotient rule problem, right? So we're going to use the rule ho d high minus high d ho all over ho squared. So we're going to have y. I'm actually going to write out each part of the ho d high piece. So we'll have y d dx of negative x minus negative x d dx of y all over y squared. Okay, so when we do this out, we are going to have y, the derivative of negative x, is just -1. So y times -1, double negative, so plus x. Derivative of y is 1 dy dx all over y squared. So we'll simplify that out, and we get -y plus x dy dx all over y squared. Okay, so the problem here is that we can't have a dy dx in our final answer for the second derivative. However, we do know what dy dx equals. It equals -x over y, because when we did the first derivative, we identified that. So what we're going to do is we're going to substitute what we know into our answer. So we'll have -y plus x times -x over y all over y squared. Okay, so now comes the simplification part. We're trying to simplify this as much as possible so that we have just one fraction and not a combined fraction. So we have -y minus x squared over y equal over y squared. So here in the numerator, we are going to need to find a common denominator. Then we're going to need to divide by y squared. So the common denominator in the numerator will be y. So we'll have -y squared over y, -y squared minus x squared all over y, all over y squared. And keep change flip, we'll get -y squared minus x squared over y times 1 over y squared. So our final answer, d squared y over dx squared equals -y squared minus x squared over y cubed. Okay, so that completes our notes for pages 115 to 118. At the end of these notes, you can now do the homework problems number 1 through 8. I want you to also complete the one problem on the left on this page. Find the curve. Given the curve y squared plus 2y equals 2x plus 1, find the second derivative of that function.